right, well, hi everyone, and thank you for attending this webinar. Today we're going to be covering the process of creating a smart 3D city model from start to finish. My name is Jeff Taylor, and I'm a 3D solutions engineer working out of Esri, Charlotte, North Carolina office. And joining me in this presentation are two special guests who I'd like to introduce themselves briefly. I guess I'd like to start with Vasu.
Thank you, Jeff. My name is Walter Pillamari. I am with PCI Geomatics, and I'm a strategic partner manager and business development, and my focus is our Esri relationship.
Okay. And then we also have Bill joining us today.
Hello, everybody. This is Bill Vedito. I'm an analyst or a product support specialist with Overwatch, supporting the lidar analyst and feature analyst extensions for ArcGIS.
Great. Well, thanks again for joining this presentation today, guys, and thanks everyone else out there for joining as well. And let's go ahead and start to dive in a little bit further. So you may be asking yourself, why 3D cities? Well, it's because our world is in 3D, plain and simple. And 3D adds value because it's easier to understand, which leads to better communication, which leads to shorter decision-making processes that save both time and money. And it solves problems that traditionally can't be solved in 2D in nature. And many people are under the influence that 3D is difficult and the 3D modeling process is highly time intensive in their mind. But this is no longer the case. A few years ago, Esri acquired a Swiss startup by the name of Procedural, who originally developed a product called City Engine. And since the acquisition, Esri has been integrating a concept known as procedural or rule-based modeling into the ArcGIS platform. And with procedural modeling, users no longer have to manually model 3D cities by hand. They can all be modeled on the fly using these procedural rules or code language. And all you need is 2D GIS data with attributes such as building footprints, parcels, street center lines, or even tree points. And leveraging data attributes that procedural rules will then transform this data into a smart 3D city model. At Esri, we're pushing 3D across the platform so that 3D models and data can be transferred interoperably between Esri's desktop products, including the new 64-bit ArcGIS Professional to be released soon, while also allowing these models 3D models to be stored on the server via 3D services, shared online as 3D base maps and web scenes, or even in custom apps with the soon-to-be-released 3D runtime. And as we delve deeper into Esri's 3D capabilities, we should start by taking a look at the value of 3D or some typical use cases. So let's take a trip to Redlands, California, where Esri's headquarters is located. And Redlands, like many other cities worldwide, have 2D GIS data. But what if we could transform this data into 3D? Well, we've done that. And we're working with our business partners and with a lot of our tools that we've developed to be able to make this possible. And what you're seeing are 3D building models provided by Pictometry for the urban area of downtown Redlands. We can include your existing building models, whether it's from another format as well, or buildings that you purchase. But we can also model buildings and things procedurally, so using these rules. So all the vegetation you see, the streets that you see, are all procedural in nature, telling you where to place cars, how tall the vegetation needs to be. And in areas that we don't have buildings in 3D, we can even create this from your GIS data or 2D building footprints. So this gives you a lot of flexibility to build out a high quality city very quickly with different levels of detail, from very high quality buildings to low level details for some of the backdrop areas. And you saw a rule being placed there and buildings generated on the fly across the entire downtown. Well, we do more than just visualizing these buildings in real world view. We can also visualize these thematically. So we can look at the zoning types or GIS attributes portrayed as color variables and thematically. We can also look at the parcel data, and we can look at setbacks. So this can be used for land use, land information. And we can preset the typical heights and setbacks and everything that these parcels need to have for the future of the cities to keep the visual character. But we can also even load on your GIS data. So we're looking at crime information or other raster data portrayed on top of the 3D city model, and we can thematically flag the buildings, for instance in this case, by commercial buildings that have the highest crime probability to happen based on historical city data feeds. But we're not just limited to visualizing the data, we can also design new developments and new communities in 3D. And this is the Redlands Redevelopment Toolkit that we've developed, which can be found on the City Engine webpage. And what we're able to do here is design how a new development would look using some basic parameters. And this is all tied in with the lead neighborhood systems. It's also tied in with the new urbanist concept of transect development. If you're a planner, you understand a good bit of these. And we can specify what the usage types of the buildings are and other information, and set key performance indicators for different things about the building. And we get these real-time reports as we change the building form, number of stories, the usage of the building, concerning cost estimates or other kinds of estimates that are vital for putting in a new development. And then when we're done with creating these 3D city models, we can export them to a web scene to share, communicate, and collaborate in 3D on the web. So we can swipe between different layers such as this before and after visual of how the downtown looked and how it looks now. And then we can also visualize a lot of other things here as well, such as comments in 3D. So you give everyone the ability to make their own comments in this third dimension. And a lot of cities need this for public feedback for new projects, but it can also be used for different mediums and requirements. So now that you have a better understanding of some of the use cases for a 3D city model, let's dive into the 3D city model creation process. So be sure to download a 30-day free trial of Esri City Engine 2013 by visiting esri.com/cityengine if you don't already have the software. Also be sure to download a 30-day free trial of ArcGIS Desktop at esri.com if you don't have a license of ArcGIS Desktop, because the 3D city creation process leverages ArcGIS Desktop's capabilities for creating, updating existing, optimizing, and enriching data that's vital for the creation of your smart 3D city model. And when modeling a city in 3D, you need data. So let's go ahead and dive into this. And data is required in both imagery or raster format and vector or shape format. And the minimum data requirements to model 3D cities are orthoimagery and digital elevation models when it comes to the imagery. DEMs, or digital elevation models, are widely available, although the height accuracy of these terrains are typically between 30 to 10 meters in elevation, with very few locations worldwide that have 3-meter height range. And if at all possible, we recommend combining lidar and orthoimagery when creating a city in 3D. With lidar, one can extract the terrain and the height of the objects on the surface of the terrain very easily using Esri's tools. Several services such as the United States Geological Survey's Earth Explorer and the National Oceanic and Atmospheric Administration's Coastal LiDAR Viewer are great resources for obtaining such LiDAR and imagery for free. So you can go there, search for your area, and then load it right in and start to work with it. And as far as vector data, if you have access to building footprints and vegetation point data, you're well on your way to creating a smart 3D city model. And at minimum, 3D cities require building footprints and, to an extent, vegetation data for creating a convincing 3D city. We also recommend streets, zoning, land use data, parcel data, and land cover, amongst other data sets. And you can learn more about other data sets that we can leverage for 3D by reading into our 3D city information model, which we'll discuss here later on in this presentation. This vector data is important as it serves as our start geometries to apply procedural rules to in order to rapidly model a city in 3D, as you saw earlier. But what if I don't have building footprints, vegetation, or even terrain data or imagery? Well, That happens quite often, and you're not alone. There's a lot of cities out there that still don't have building footprints. So I've invited Vasu Pulamari from PCI Geomatics and Vil Vitido to present with me in this webinar for this reason. And Vasu will begin by showcasing PCI's capabilities for extracting terrain from both aerial and satellite imagery. Bill will then disclose Overwatch's capabilities for extracting features from lidar and imagery for use in the creation of a smart 3D city model. So I'd like to hand off to Vasu to start to present on basically some of the awesome things that PCI can do with imagery.
Thank you, Jeff. First of all, I would like to thank Esri for allowing PCI the wonderful opportunity to be part of this webinar. Hello, everyone. My name is Vasu Pulamari, and I am based out of Redlands. And as stated, I'm PCI's strategic partner manager for our Esri relationship. PCI Geomatics is a world leader in imagery processing software with headquarters in Gatineau and Toronto, Canada. And for those that may be new to image processing or that don't know exactly what image processing means, PCI specializes in taking imagery, raw imagery, and georeferencing it, pan sharpening, color balancing, and atmosphere correction in order for a mosaiced or stitched product in order for it to be used for other ArcGIS workflows. Also, PCI has software for allowing a user or individual to take the imagery and to extract features, to figure out changes between two images of different dates, and furthermore, even to color, to do classification in order to support specific plans and land use plans. PCI also has offices in USA, China, with 60 resellers worldwide. PCI is also a gold partner with Esri, and we specialize in creating automated and scalable solutions for any size project. Currently, there are more than 25,000 licenses of our PCI product suites worldwide. Esri used PCI's enterprise cloud solution to deploy 5 million square kilometers of imagery onto ArcGIS.com. And we're further exploring opportunities with Esri on using our technology to support the ArcGIS platform and strengthen imagery workflows. Finally, we're working with Esri, MDA, and RapidEye on the Natural Resources Imagery Grant Program to show the value of using radar, satellite, PCI imagery processing solutions, and ArcGIS platform to show fusion of radar and satellite data, as well as illustrate to Esri customer base that imagery is more than a base map. PCI supports both aerial and satellite workflows to generate terrain models. Even though there is automated processing within PCI's desktop flagship product called Geomatica, there's certain data requirements needed. With aerial imagery, Geomatica is able to create terrain from imagery that has been collected with a 60, 80, or more overlap, and the requirements for satellite are that they must be a stereo pair. Generally, most data providers will bundle stereo satellite data for DEM extraction separately. And generally, stereo pairs are a left image and a right image that needs to be combined in order for the terrain modeling to happen. Also, PCI prefers same-day, same pass, but it's also possible to do a different day and different pass when it comes to satellite data requirements. Prior to running the DEM or the terrain modeling process within Geomatica, there are several requirements that are needed with both aerial and satellite imagery. Generally with aerial imagery, since it's camera-based, there is a interior, exterior orientation. There is a process called aerial triangulation, and you would also need to have the raw TIFF images. With satellite, it's a little bit more straightforward, where you would need to have the stereo codecs or the left and right images, along with RPC coefficients. RPC is a minimum level of georeferencing that most satellite providers provide with the data, and that you could use within our Geomatica product to further refine the data prior to doing the DEM, which we will cover in the following slides. So PCI's flagship product, as I said, is called Geomatica. And Geomatica is widely successful in Canada and worldwide. One of the functions in Geomatica is auto DEM, which you're seeing right now in the screenshot. Auto DEM is used to create DEM, digital elevation models, DTM, or digital terrain models, and DSM, or digital surface model layers automatically from both aerial and satellite imagery. Terrain modeling is needed to create accurate 3D models for building and city build-outs. We'll now dive into the process of how actually the workflow happens. So right now we're seeing workflow with satellite and aerial imagery. The first step in creating terrain modeling is to ingest the data, georeference it, and create a seamless mosaic. With aerial and satellite imagery, the workflow is different. Since aerial imagery already has what they call calibration coefficients, which include exterior orientation, interior orientation, along with aerial triangulation, the process of creating a seamless georeferenced mosaic or an image that's stitched together is easy. As the calibration, the exterior orientation or EO, the interior orientation or IO, and the aerial triangulation provide an easy way to georeference the image. With satellite imagery, it's a little bit more different. With satellite imagery, georeferencing has been sort of done, With satellite imagery, georeferencing has to be done by selecting ground control points. In the previous slide, we mentioned the fact that there were RPCs, or minimum level of georeferencing that the satellite provider has given to the image. In order to perform terrain generation, the satellite imagery needs to be georeferenced. The RPC model can be used to refine the imagery to a more accurate state, after which a seamless mosaic can be created or stitching the various images together. Now comes the process of taking that ortho mosaic and to create a DSM, DTM, or DEM out of it. With auto DEM, it automatically computes the elevation for top of all features. Essentially, the algorithm combines the stereo pairs for satellite imagery and air photo images to create a seamless terrain model with the orthomosaic data set to drape over the terrain. And this slide is sort of showing there's the three types of terrain models that can be created with this process. There are normalized digital surface model, which can be used to derive feature heights and vegetation derived from calculating the difference between two elevation outputs. Digital surface model, which models surface height above sea level, and the digital terrain model, which is used for 3D modeling. So now let's dive into some examples of products. So in this case, here's an example of a satellite imagery with overlapping stereo pairs that have been merged together at 15 centimeters resolution, and it's been auto-rectified and mosaic together. Now out of this, using the AutoDEM and the processes that we just spoke about with PCI software, we can create a DSM. So this is a DSM generated from the previous slide at 45 centimeters. And we could clearly see where the buildings are. We could clearly see where the elevations are. And from there, you know, where the road build outs are, and various other features here. And finally, this is a DSM result from taking from this satellite imagery, and it's been processed to create this type of a normalized DSM that we're seeing over here. And now that we have the DSM or DTM and DEM with PCI technology, we can now use Overwatch to further refine it. Thank you, everyone.
Thanks, Basu. So at this point, I'd like to hand over to Bill Vitito to discuss a little bit what Overwatch's tool feature analyst can do for extracting features from imagery.
Okay, there we go. Okay, so again, I'm Bill Vitito with Overwatch. I'm based out of Missoula, Montana. What you see, let me go back one slide here. Well, my keys don't seem to be. Jeff, can you go back one slide for me?
Here we go.
Okay, so we've got the Feature Analyst web page here, and basically Feature Analyst is an extension for ArcGIS, as I mentioned earlier. This web page is at overwatch.com. You can go there, take a look at our products, watch some videos. You can also download Feature Analyst or lidar analyst, and then we'll supply you with a trial license to try out Feature Analyst and lidar analyst on your own data. So Feature Analyst automates the extraction of features from satellite and aerial imagery. So we extract features such as forest canopy, tree points, water bodies, buildings, and roads. And our next slide, whoops. Sorry, Jeff, I messed you up there. Our next slide, I think my keys are working now. So this shows the Feature Analyst setup learning window. So the basic idea behind Feature Analyst, if you look up in the top right-hand corner, you can see our Feature Analyst toolbar. And the basic idea is you give Feature Analyst training sets. In this case, I digitized examples of trees. And then you open a setup learning window for that training set. And then you give Feature Analyst the parameters that you want it to use. And then Feature Analyst goes into the image. It uses machine learning. It finds out characteristics of your training set, and then it goes into the full image and returns other trees in this case. So you can see those tree points in the background that are, they're loaded in the workspace in grain. Then we'll go to the next slide, and here you can just see a zoomed in area of those tree points. And in this case, when I was extracting the tree points, I just masked out the buildings, which is another feature of feature analysts, that you can mask out areas, or you can just look within areas of interest. And this does create a model. I won't actually show that procedure, but it does create a model that you can then batch to other images, other similar images, and just automate your workflow.
Okay, so we briefly talked about how you can create terrains if you don't have them, and how you can extract features from imagery. So just with imagery and with lidar, whatever it's extracted from, we have some tools for adding the heights to your building footprints and your vegetation points. And this is one of the older workflows for ArcGIS, creating random points, adding surface information, running summary statistics, and joining the data. And this would and will allow you to automatically add heights to these features. But if we take it a step further close out of these tools can be downloaded as part of the new 3D city information model that we're going to cover here in a little bit in the presentation for automatically calculating these heights. And to apply 3D height information to your building footprints, all you need is a digital surface model and digital terrain model, or your digital elevation model, pretty much. So this is the final result of the work that we did with PCI and with Overwatch. So you can see the buildings extruded into 3D, leveraging the height data from that digital surface model. You can see the vegetation leveraging the height data from the digital surface model as well, and the typical shapes and genus species of whatever green or deciduous trees would be in this respective location. And what we've also been able to do is drape the imagery on tops of the roofs of these buildings to add higher realism, and then define buildings that should have certain roofs based on their usage types, such as residential versus commercial buildings. And this is all exported into a 3D web scene, which can be shared with anyone on the web. So let's take it a step further. We've talked about imagery, now let's talk about lidar. And we're going to talk about extracting features from lidar if you don't have existing building footprints or other information. So Esri has some key tools for extracting terrain similar to what PCI showed earlier from imagery. And what we're able to do here is use the LAS format, put it into a LAS data set on the Esri side of things, and then select the classes that we want to have returned. And by selecting certain classes, we can choose from just the ground points, which gives us the ground or the digital terrain model, your elevation model there. And then we also can enable all returns and get the surface points, or the maximum height values across that point cloud. And so this is another tool that we have, which allows us to convert that last data set directly to raster, and then we can inherit those height values from those raster data sets to tell us, okay, give us a terrain that we want to put the buildings on in our city on, and then also give us the height data. We want to derive the heights for the vegetation, trees, and other urban elements for our city. So I'd like to hand back over to Bill to talk a little bit about the 3D extraction capabilities of lidar analyst for features.
Okay, thanks, Jeff. So again, lidar analyst extracts features directly from lidar, and any lidar format really. LAS, you could have bare earth rasters and first last returns. So it extracts buildings, trees, and other features from the lidar data. So the screenshots and movie you see here show features extracted from Charleston, South Carolina. This is public lidar data that's available for free download at the USGS site. It has this particular data set has fairly coarse point spacing. That's one thing that lidar analyst isn't picky. It'll work with any lidar data, any point spacing. Now, typically we prefer point spacing that is 1 meter or less, and that's best for getting small buildings. but again, we'll work with just about any lidar data. So in this example, lidar analyst was used to extract 3D buildings, forest polygons, and tree points. And then those features, well, the buildings and the tree points were put into Esri's city engine model, which is shown on the right. Okay, so next we'll move to some city-specific lidar. Now this is lidar data for Charlotte, North Carolina. And again, we're going to take this lidar data, LAS files, and we'll generate the typical lidar analyst workflow, bare earth, then we'll extract buildings and trees from it. So let me go to that next slide. There we go. So again, this is the first step. Lidar analyst has a simple workflow. It starts with extracting the bare earth. So we're basically going to, the bare earth is what's left after you remove all the raised objects, such as buildings and trees. And you can see on screen here on the left, the bare earth extraction dialog. And at the top, we just point to the LAS file we want to use. Lidar analyst automatically detects what the horizontal and vertical units are. It gives us a suggested point spacing or output cell size. And then we have a couple of different methods to select from. And you can see I've got checked here to use the existing ground points that are already identified in the LAS file, which speeds up things quite a bit. But we can find them ourselves, but it is quicker to use what's already there, if they're there. And then we have some pre-processing options. So then we would just click OK once we have all that set, and lidar analyst would go through and extract the bare earth. And what you see here is actually a bare earth hillshade that we generate as a second step. So you can visualize that bare earth layer in 2D. And then our next slide. So our next step in the workflow is just to extract buildings. So we use the bare earth layer that I showed in the previous slide. Again, if you look here, we've got the lidar analyst toolbar. This is the bare earth extraction. This is the building tool. So we open the building tool, and in this case, if you've lidar analyst automatically detects any bare earth that you have in the table of contents. So it defaults to your bare earth. It knows where the LAS file where that bare earth came from. So we'll use both of those layers, and then we have a couple of extraction methods. The first is a raster-based method. The second extracts buildings directly from the point cloud. And so we just left it set to defaults. Click OK, and then what you see here in the workspace, the red are the buildings returned from lidar analyst. And again, these are 3D, and they have other attributes such as building orientation, average height, that kind of thing. So then the next step in the typical workflow is to extract trees. And so we just click the tree tool. This opens this interface. Again, it detects the bare earth automatically and the LAS file. Typically, we would mask out the buildings. I don't have it selected here, but typically we would. And then I just use the default settings. We have a couple of different methods depending on the types of trees that you have, and the type of forest. And then you just name your tree points and your forested areas, so you'll get the actual tree points and also the polygons for the forested areas. And in the workspace, you can see back here the results of that. So the forested regions and also the individual tree points. And these are just three of the tools that we extracted the features such as contour lines. I'm not going to run through those, but let's see if I can get to the next slide here. Jeff, could you forward that? It seems to be stuck. Okay, so this isn't really a step in the workflow, but it is. This shows our lidar analyst 3D viewer. So this is a separate application. You can launch it without having ArcMap running, but it can also be closely linked with ArcMap. So in this case, it's really handy to view your buildings, your final output, in your point cloud, so you can just check your buildings, visualize them, and other features such as trees, forested areas. And you can also, I said they were closely linked, you can zoom into a particular area, say in your point cloud in your 3D viewer, and then sync your ArcMap viewer to that extent, or vice versa. Go zoom into a 2D area in ArcMap and then sync the 3D viewer with that. And Jeff, oh, let's see, we have one more slide. So I clicked it, so I'm not sure if it's going to work.
All right.
Okay, so just to sum up again, this is what lidar analyst extracted from this Charlotte, North Carolina data set, which is a little bit higher quality than the South Carolina data set we looked at earlier. It extracted building footprints with heights, vegetation data with the heights. We also extracted bare earth, which was used to extract those buildings and tree points. Jeff, I'll pass it back to you.
Awesome. Thanks, Bill. Well, hey, thanks for joining again, guys, and showing us the value of extracting features. And what we're going to do now is show you the value of once you have these features, what you can do with them and how you can create your 3D city. So this is that original data set that you saw as LiDAR originally. What we've done is draped an image on the terrain, and we have procedurally generated these 3D building models using Esri City Engine rules. So those City Engine rules leverage the GIS data attributes and automatically create this area of the city in 3D. And then again, this is from point spacing of 3 points per meter, whereas you saw with the USGS LiDAR, that's typically 1 point per meter. And they both are fairly accurate to what you see in the environment. There may be a few cases where the vegetation is not exactly like it is, but there's always manual pieces involved with feature extraction there. So you always have to keep that in mind. So if we were to zoom in to this model a little bit closer, I'm going to show you another pretty cool thing that we can do with our 3D models. So we just released this plant library. It's part of something that Lumen RT provides. And we have 80 somewhat genus species of plants in this library that contain all sorts of information, but we also know what the typical volumetric forms of these trees are. So we can visualize this in 3D, just like we could visualize buildings thematically by colors, as you saw in the video earlier. And each one of these contains information. So if you select on anything in these web scenes or on our newer online globe services that we're going to be releasing, you'll be able to see the data attributes and even query this information. So that's could be one of the final results of a derivative from LiDAR transformed into a smart 3D city model. So that's the end of the first part of the presentation. I want to quickly dive into our second piece here. So let me zoom in a little bit. Once you have all your GIS data necessary to create a 3D city, the next step is to make sure it's in a format that can be loaded into Esri City Engine. And City Engine can import raster imagery in the GeoTIFF and JPEG formats. Using ArcGIS Desktop, you can easily convert your existing imagery into those formats as well. Geospatial vector data as shapefiles or geodatabases are also supported in ArcGIS Desktop. However, we are highly recommending users load the data into Esri's new 3D city information model. I'm about to tell you a little bit more about that. And this is honestly where a lot of the magic is going to happen to save you time with creating your city in 3D. This 3D city information model is Esri's new enterprise 3D geodatabase format. And leveraging tools accompanying the data model, one can transfer data from CityGML, the local government data model, your custom geodatabase, or other formats directly into the 3D CIM. All it takes is some small modifications to some of these tools to connect your data to the new schema. And this data model is important as all our new City Engine rules, Esri develops, align and work directly with the 3D City information model attributes out of the box. So let's say you're using one of these other data models or a geodatabase that's custom to your city. You can pre-write the connectors to connect to this 3D City information data model, and if they're all connected, all you have to do is press a button and it will update one database to the updates from the other database. When you update your city's data, it will automatically update your 3D model using those tools. So where can I find this 3D city information model? Well, you can download it from the Esri GitHub site and begin working with it today. Just search for the keyword 3D to navigate to the 3D cities template, download location. You can either clone it to your desktop or download the zip file. And if some of you are used to using GitHub, this is a great way to stay informed of updates to this information model as they happen over time. So, and once downloaded, you'll be able to access and utilize the 3D CIM geodatabase schema for your projects, as well as other new tools such as the calculate building heights geoprocessing tools that we discussed earlier, and the vegetation height and canopy shape tools in there as well. So let's create our own 3D city model. So once we have all of our data formatted, it's all cropped to the area that we want to model, it's put into this local government data template or your own geodatabase, we can then load it into City Engine. So I've created a project called Redlands, and I'm just going to grab my imagery and paste it into a maps folder inside of this City Engine interface under the Redlands 3D CIM project I just created. And I'm also just going to copy and paste my geodatabase into the data folder. So now everything can map very easily, and I can create a 3D model of a specific area of my city very quickly. So I can drag and drop the terrain file into City Engine, and then I can specify the image to place on top or to drape on top of the terrain, and it automatically loads that data into the viewport. So give it a couple seconds, and now you see the terrain loaded. So it can load both metric, imperial, whatever your GIS format is, it'll bring it right in and project in the right coordinate location. So I can just drag and drop my geodatabase in, and I can then specify what layers that I want to bring in. Well, maybe I don't need the parcels and the area of interest that I chose to clip everything to. I'm just going to load the other data sets in, buildings, streets, tree points, and they automatically place them in the scene. So one of the steps, if the features do not have height data associated with them, we can easily just align them to the terrain using some simple tools inside of City Engine that you're seeing here. Just projecting, let's say, the trees to the terrain, and then we can then project all the streets to the terrain as well. There you see, project all to the terrain, and it automatically places those on the respective terrain image layer. And if you want to get some of these City Engine rules that we're going to apply to the model, you can go to the City Engine Resource Center and download the new vegetation library that you just saw there, or you can go to the Resource Center and download other rule files for creating your city in 3D. So now that we have everything projected to the terrain, I'm going to then copy and paste some data files or some rules and assets associated with these rules from another project into my new project. You can reuse rules from other projects. You don't even have to drag them into this new project. You can just drag and drop them from other projects into your project as well. But you have to remember where you pulled them from so that you send all the files necessary to other people working on the project later on. So now that I've put those rules in the project I'm working on, I'm going to select the transportation segments as an example. And I'm going to assign the essential street rule to it. And what this is going to do is automatically procedurally generate streets for the entire downtown area of Redlands that we've cropped out here. So you'll just give it a couple seconds, and it's all generating on the fly in the back end, all of the street networks, and they leverage the width of the city's data set. So if you already have attributes for how wide and the number of lanes, we can inherit those values and have the streets build themselves accordingly. And if there's any errors with the streets, as you see right here, for instance, we can then do is select some of the editing tools and manipulate anything. So we have editing tools to draw building footprints. We have editing tools to draw points. We can even edit your street networks and move them. But if the edit doesn't work by just moving a point, for instance, we can redraw that network and update it, and it will still retain the original attributes that we had in the GIS data in most cases. So I can start to draw that center line again. And that's just a really quick fix in some circumstances. And this is really good for planning and urban design. If you're creating new development, you can use the same concept to help with that. And I can even resolve conflicting shapes where things may overlap. So now that we have our street network, the next step that we want to do is select all the building footprints. We want to generate these procedurally with a procedural rule. And I want to show you some new rules that we've been working on. So this is an essential building rule, and these will be released here in the next month or so. And what we're able to do is link to the GIS data attributes that we've pulled from the lidar heights and really recreate the stuff procedurally in 3D. Now you may notice there's some artifacts with some of the building heights, whereas they're not what they should be, and that's always the case with applying lidar heights to certain features. You may have to manually go back and just change the attributes on a few of the building footprints as necessary. But a lot of the times it will not have issues. The other thing that we can do is display these buildings as just solid white. We can put textures on them. We can inherit the color values from the terrain. And that's what we're going to kind of go through here right now. So there's a lot more than just having the model. You can link it to other data layers. I can, for instance, link this to my imagery file, and it will automatically pull the Z, X, Y extents, and we can then color the buildings according to the RGB values of that imagery. This could even be a GIS analysis layer. We can color any kind of GIS features using these kinds of rules to and link it to that raster data set. So then we can map, like you just saw with the terrain color, make sure they're all mapped, the RGB channels. And what I'm going to do is just let's make the buildings the terrain colors. This is more lightweight. It doesn't have raster imaging on top of the buildings, keeping the polygons very small and the final model output small and lightweight. But if we want to, we can even drape the aerial image directly on top of the rooftops for more added realism, and even choose from a directory of textures to apply to the sides of the building facades if we really wanted to. So now that those are all complete, what we want to now do is select some of the vegetation information that we have in this 3D city model. So what I'm going to do is go over to this one location on my scene window, and I'm going to select all of the objects in the same layer for the vegetation points. And I'm going to assign a rule for the essential plant loader rule, and this uses those LumenRT trees that we discussed earlier. So I'm going to select the tree, and I'm going to use, let's say, the symbol name or an attribute to automatically connect to the correct genus species that tree really is. And if I don't have height data for those trees, I can even let the genus species determine the maximum height of what that tree type typically is if the city has an inventory of that information. So it's as smart as what you plug into it, pretty much. And this is what the final model looks like for the downtown, just created from existing 2D GIS data procedurally. If we zoom around, you can kind of get a better feel for it. Okay, so the next thing is, what if I have existing buildings or existing 3D models? Well, you can take them into the multi-patch format, or we can drag them, drop them into CityEngine as collada models. And what I'm doing right now is loading buildings from Pictometry. So these are 3D buildings for Redlands. And it just adds that higher realism where there are iconic buildings in the downtown that we want to be able to visualize that character. But you can couple those with your 2D GIS data that's been transformed procedurally into 3D to be successful there. And then export that in the very end to a web scene. So enough talking about creating a 3D city model. Let's talk about 3D base maps and where Esri is going in the future. So let's go back one slide. ArcGIS users will soon be able to share their 3D cities and data at different spatial and temporal scales. And Esri's 3D base maps are a brand new distributed service unified on a 3D globe. These 3D services will support thematic and realistic visualization at all scales. So At the site-wide scale, Esri's 3D city base maps provide your city with the foundation for your 3D city, context for your 3D projects, a canvas for your analysis, and the ability to share your smart 3D city via apps to a global community. So what you're seeing is 3D in a web browser pulling data from distributed online services. And at worldwide scales, we can assess global impacts such as hurricanes or other things that could create large-scale risks or other GIS data. But let's fly over to Switzerland and take a look at avalanche danger zones. So this is 2D GIS data placed on a 3D surface, and it contains attributes. And we can even visualize text as well in 3D, and it follows the camera. And these 3D web browsers were also built to cache high-resolution imagery and terrain, as you see here. And they load higher resolution imagery as you zoom further in or to different extents. So now let's visit San Francisco. So let's fly back to the global scale and kind of pan around and slowly navigate into the downtown area of San Francisco. So we'll just pan over and zoom to the city. And these 3D services can load both procedural buildings and highly accurate third-party models, such as 3D building models from PLW ModelWorks that you're seeing here. And notice as I move around the city, the 3D web browser pulls 3D content as necessary. And attributes from GIS data, such as street names, can even be displayed in 3D. And when you pan around, these names will automatically follow your position that you're in. So buildings slowly loading as you move throughout an urban area. And these will also be more than just buildings. You'll have other features that can be located and queried and panned to in 3D, et cetera, when we release this publicly. So let's go to our last stop in this 3D tour, and we're going to visit Portland, Oregon, where our development team has been doing a lot of work with analytical volumes of buildings using the 3D city information model. So in Portland, analytical trees and buildings are leveraged to assess sustainable factors such as 3D regulatory volumes or 3D zoning volumes, the placement of a new building, solar potential, or even shadow impact studies. And what we're seeing here is that new building in 3D in correlation to, does it fit within a zoning regulation for setbacks to keep the character of that urban core? And we can also look at, those solar impacts in that third dimension, as well as shadow studies, as I mentioned, of the vegetation points. Okay, so in 2014, our development teams have a unified goal of bringing 3D to life across the ArcGIS platform. And this full integration between desktop, server, online, and apps opens new doors for GIS analysis while also creating new 3D modeling and data visualization capabilities. So I'd like to invite you to begin creating your own smart 3D city model today. And if you haven't already done so, be sure to visit the esri.com/cityengine webpage and download your own free, fully functional trial of CityEngine Advanced for 30 days. And on behalf of everyone at Esri, I would like to personally thank you for attending this webinar. And I'd also like to thank Bill Vitito from Overwatch and Vasu Plamari from PCI Geomatics for presenting with me. Also, feel free to send me an email at gtaylor@esri.com if you have any questions concerning modeling your city in 3D and maybe have some questions about where to start. And at this point, we like to open the doors for questions. So if anyone has any questions, feel free to type them in the question box and we'll get to them accordingly. If you have questions for Bill or Vasu, feel free to leave them as well. So let's go ahead and jump forward here. First question, are there examples of procedures available in CityEngine to model buildings at floor and room level? Yes, there are, and you can find some of these, I believe, in our 3D city information model, where we've taken some campus information in and procedurally modeled it in 3D. In a lot of cases, they're very simple rule functions where you just tell it to extrude, and you can apply those to CAD features. But you can, for instance, take DXF into CityEngine and model that in 3D. So in other questions, this maybe for you, Bill, sometimes buildings are covered by trees, and they make it hard to see the whole building. Will the, will the technology that Overwatch have be able to solve this problem?
Well, I assume that question is for lidar. Because with aerial imagery, there's really not, you know, a good way to see under the tree unless it's leaf off. But the same thing holds true for lidar. You really want lidar that's been flown with leaf off conditions, ideally, so more of the lidar penetrates, you know, through the tree structure and gives you better, you know, building outlines. Now, when it comes to you know, evergreen trees that are right up against a building, those can still present problems. But generally, you know, you get returns with leaf off that allow lidar analysts to get good building outlines.
Okay. So on that same note, is the building data set created from Overwatch lidar analyst positionally better than traditional stereo pairs? I guess lidar versus stereo, pros and cons. Any, any thoughts there, guys?
Hello, this is Vasu. I believe with stereo pairs, I think there's a certain amount, it all comes down to cost really. With imagery, if you get raw imagery with stereo pairs and using PCI product suite, I believe that there will be a certain more efficient processing and efficient cost versus potentially with LiDAR. But in the end, it all depends on budget and how to sort of allocate accordingly.
Okay.
Yeah, and I don't really have a background in stereo pairs, extracting buildings from stereo pairs. You know, I will say with the, you know, more and more LiDAR data is available for free from state, local, federal agencies and it's getting to where it's a very high resolution, very good point spacing, and so in those situations, I would, you know, I would think that lidar analyst is a very good option.
Okay. So I have another question from Hussein. He only has a digital elevation model for a project and not a digital surface model. Would this work well with that? And actually, you can create a 3D city model without the digital surface model. It's a real value added to have it because it really speeds up the accuracy of what your buildings can be. But if you know the typical tree types, they all have a limit to growth, and we have a lot of those plugged into our rules, and you can code them further or work with what's existing. But then also for the buildings, if you know what the number of stories are or have that already in the data sets, you're good to go. If not, you can use the usage types of the buildings to determine the heights to make all the buildings for your city, and then slowly go through and update that over time as necessary. That's a really good question. Let's see, what else do we have? You have to bear with me. This is a very small window I'm reading questions from. Can I use Google Earth data or Google Earth type mobile capture systems to auto texture the exteriors of buildings? No, we've done some testing with different mobile systems. Don't want to comment on certain ones, but there are issues where if the spatial locations of where they say that the images are off by 5 to 10 meters, it's very difficult to texture those accurately on the sides of buildings. So that's a typical problem you run into. Can you export the 3D model into Rhino, 3ds Max, or other platforms and vice versa? Yes, you can. We can export 3D city models into a lot of different platforms. The best approach is FBX format, and that goes well. We also have Python scripted export capabilities from CityEngine as well, and other things there. So are there any planned training workshops for CityEngine in the works? From Greg Dobson. Yes, Greg, actually there are. We have several different training courses that we're putting online. If you go to the Esri training site, you'll notice that there are some for the 3D city information model for how to get data into it. We have other training that we are developing with education services for how you can create a smart 3D city model as well. Is there a plan for supporting the Oculus Rift and other 3D virtual reality headset solutions? So John, we already do support Oculus Rift. We have a business partner out of Europe that has put together a workflow for how to export using the Python scripted export from CityEngine directly to that. And we've done other projects with the entertainment industry to do just that as well. So we have a lot of success doing that. And we actually took that model of Redlands and put that into the Oculus without any real issue as well. So the CityEngine work with Google Earth, yes, you can load models in some ways onto there, but keep in mind we are releasing our 3D runtime. You can have very high quality terrain and other information onto that and load your entire city and all the attributes and everything's intelligent in our new 3D services. How can we generate the roofs exactly as they are in real context when we have the LiDAR data? Well, that's the quality of your LiDAR data is going to determine that, and all you need to know is the height of the base of the roof versus the maximum height of the roof. And those tools can be leveraged that you see within the 3D information model to do so. Just put a minimum and max height for the start and end of the roof in those respective data sets. Let's keep going through a few more of these questions. I know we're going over a little bit on time, but I just feel like there's a lot here that people want answered. If we don't get to all these questions, we'll answer these by email as well. Let's see. So can we use BIM to create building interiors using CityEngine and carry indoor positioning? Save Software just released a plugin to go directly from Revit to the geodatabase, so look into that. That'll streamline your 2D to 3D needs there. And you can apply procedural rules to that data once it's inside of CityEngine. The web viewer is currently in HTML5 and JavaScript, and it uses WebGL technology. The same thing with that 3D globe service that you're seeing. Our 3D runtime will use the same capability, so you'll be able to customize that runtime for your needs if you are a developer. And I think that's pretty much it for today that all we have time for. Again, thanks everyone for attending. Vasu and Bill, thanks for joining in and answering questions and discussing how you can obtain data or create data if you don't have it from existing information. And everyone have a great afternoon.